Okay, you guys, just to let you know, I am recording now. Okay, so it is happening. Okay, so I just got something from you, Zach. It went up on the screen briefly, but it faded away real quick. So I'm not sure uh, if your question was something you want to talk about immediately. I'm not able to see it right now. Let's see. Oh yeah. Okay, great. I got it, Zach. Good. All right, so let's go to this setup. Trigonometry. Remember, um, the first three letters of the word trigonometry are TRI. It's got to do with a triangle. Right triangle trig is what we're basically going to be talking about for the most part when we're talking about trigonometric functions in this class. And the main idea is, remember SOHCAHTOA. I don't know if some of you may have never heard of that, but the idea is it's a breakdown of the definition of sine. How do you determine the sine function? Cosine, C is for cosine, T is for tangent, S is for sine. And the idea is that it's based on the triangle, you know? So if we were dealing with a 45-degree angle, I'm going to go to the unit circle right here. Notice it is a unit circle. So that means the radius is 1. Let me do a 45-degree angle, okay? So, and the triangle we're talking about is this one right here. That right triangle right here. And when you're at a 45-degree angle, this is 45 and this is 45. So the sides are exactly the same. So if this was our x coordinate over here and this was y, the values that we calculate for sine and cosine and tangent are all based on the unit circle. It's kind of like the same ratios will work in other radius as well, but the unit circle is the foundational perspective of it, where the radius is equal to 1 on that circle. And if you remember 45, 45, 90, the length of the side on x and y are the same. And anybody remember what the values are for x and y, the length of the sides?
Square root of 2 over 2, square root of 2 over 2.
Exactly. Very, very solid. Good stepping up. I appreciate it. Square root of 2 over 2 and square root of 2 over 2. And if you notice that the x value, notice what's right above it here. When you're dealing with this, cosine, notice, is adjacent over hypotenuse. And if you're dealing with this angle down here, in this corner, adjacent is the x coordinate. Cosine is x. So when you're on the unit circle, this is the x value. That's the cosine of the angle. And this is the sine of the angle, the y value. And it turns out they're both the same with that situation, so there's no big news there. But the idea is when you go around the unit circle, if you're down here at 0 degrees, and again, most of the time we're going to be talking about using radians for the answers. So for the angles, what we're working with. So we're talking 0 degrees or 0 radians. And make sure you're conscious, you guys, when you're on your calculator, whatever you're graphing, or whatever you're using, make sure your mode is in whatever it is you're working with. And typically it's going to be in radians. I might talk about degrees at the beginning here to get people back on board, but most problems that we're going to be working with are in radians. Most science and business are talking in terms of radians and that kind of stuff. So, so remember this. Part of the issue of this situation is we got a right triangle. Pythagorean theorem is what allowed us to get square root of 2 over 2 and square root of 2 over 2 for the sides. Remember this. Remember, Pythagorean theorem is a squared plus b squared equals c squared, or in this case, x squared plus y squared equals 1. Or we've got cosine squared theta plus sine squared theta equals 1 squared, which is 1. And notice the notation that the 2 on cos and the 2 on the sine, that's the same as saying cosine of theta squared, okay? So if you haven't seen that notation before, it takes a little bit to get used to it, but it's something that we're typically be writing it in that sort of a fashion. And if you take square root of 2 over 2 and you square it and you add it to square root of 2 over 2, you'll see you get 1. So it is a matter of applying it. And remember, the 38-degree angle and the 60-degree angle, are kind of special. They've got special coordinates that are consistent across the board around the circle. The 30-degree angle and the 60-degree angle are going to be showing up all the way around the board. And if you can get the pattern down, it'll save you. You won't have, it's not super helpful, but you can get the pattern down and recognize that everywhere around the board, you can kind of get a sense of what the sine or cosine are. And it's kind of a benefit to being confident with your material and that kind of stuff. Notice this, that all the way around the circle, a 45-degree angle is in the first quadrant. If you go to the second quadrant, the same representative angle here, that's a 45, 45, 90. It's the same coordinates, but it's just what quadrant it's in determines whether it's positive or negative. So in this case, we're going left, the x coordinate is negative, so the cosine is negative, and the sine is positive. Down here, negative, negative. Down here, cosine is positive. X is negative, the y is negative, the sine is negative. Cosine is positive, sine is negative. So it's a matter of remembering what those situations are and from refamiliarizing yourself if you haven't seen it in a while. And over here, the cosine is negative and the sine is positive. Okay, here we got positive, positive. Okay, so notice as we go around the circle that zero, when we're talking radians, remember what a radian is. Let me just do a quick review of this. Remember that if you take the radius of the circle and swing it up onto the up onto the curve, the circle itself, that length is 1 radian. That is 1 radian. Second radian would take us over here somewhere. Okay, and the third radian would take us here somewhere. And notice that 3.14 yada, 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 the infinite decimal, radians is right on 180 degrees. It's a 180-degree angle. That turns out to be 3.14, or pi radians. Again, remember, pi is not 3.14. It's an infinite decimal, goes forever. We have a tendency to say 3.14, and if I ever do that, it's not 2 decimal place number. It goes on forever, okay? Remember this, so half of pi is pi over 2. So we're up here at pi over 2, that's half of 180. The 90-degree angle is up here at the top, which is pi over 2 radians. You add 90, you get 180. Add another 90, you got 270 degrees down here. And that's 1 pi over 2, 2 pi over 2. This is 3 pi over 2 radians. Okay? And this turns out to be 4 pi over 2, or 2 pi radians, or 300, let me put 360 degrees there. I'll put that also. Okay? All right, so that's getting the orientation down of when I'm talking about 0 degrees, we're talking about 0 radians. 90 degrees, I'm in the table now. 90 degrees is pi over 2 radians. 180 is pi. 3 pi over 2 goes with 270. And 2 pi goes with 360, all right? Well, notice the value of the sine and the cosine at each of these spots. I'm going to draw a picture of the curve. I want you to remember that, get a feel for it. Remember, you can use your calculators. If you forget, plug in cosine, graph it. Plug in sine, graph it. You should be able to get it. Remember, the cosine is the x and the sine is the y. But at 0 degrees, if you notice, the x value is 1. Cosine, that's the cosine. So at 0 degrees, x is 1. At 90 degrees, pi over 2, x is 0. At 180, x is negative 1. At 270, x is 0. At 360, we're back up to x being 1. And now going up to the sine function, the value of y, here at 0 degrees, y is 0. Pi over 2, we're up at y is equal to 1. Pi, we're at y is 0 again. 3 pi over 2, our y is down to negative 1. And then it's back up to 0 when we're at 2 pi. So remember with the graph now, this is where the graph comes from, how you determine it. Make sure you're confident with that. So I got the sine first, let's do that. At 0 radians, the value is 0. At pi over 2 radians, the sign is 1. At pi, we're at sign is 0 again. At 3 pi over 2, we're down to -1. And at 2 pi, we're up to 0 again. And remember, when you see a picture that comes up like this, remember, this is going on forever. You know, this does not stop at 2 pi. And it doesn't stop. So at negative pi over 2, it would be down here. You know, it would be that setting. And at 3 pi over 2, 4 pi 2, at 5 pi over 2, it would be up here. Okay, so it would continue on forever in both directions. Now let's go down to the cosine. Cosine at 0, we're at 1. Off of the midline. Notice it's up, it's off. Sine is on the midline at the start. Pi over 2, we're at 0. At pi, we're at -1. 3 pi over 2, we're back up to 0. And 2 pi, we're back up to 1. And again, we've got a curve that's going on forever here. And again, it goes on, you know, and it comes on, and whatever that, it doesn't end, but from 0 to 2 pi is one, we call a period, you know, the length of one full cycle. And that is the graph. So remember, cosine starts off the midline. The positive cos starts up at 1 when you're on the unit circle. And when you are down on, and the sine function starts on the midline. And the positive sign goes up from the beginning, okay? So recognize if it's going through the 0, 0 and it's going down, recognize that's a negative function, or, you know, there's a variety of different ways you can represent the function. Okay, so one of the things I want to point out is this. These two identities here, the limit as theta goes to 0 of sine, the sine function, so as theta goes to 0, as I'm coming into 0 from the right, and if I'm coming in from 0 to the left, it is 0. So the limit is 0. Cosine, as I'm coming in from the left, and I'm coming in from the right, where they're both going to 1. So the identity is called the limit as theta goes to 0 of cos theta equals 1. So the one that I really want to talk about now is this. I've asked, there are several problems in sapling that ask you to use this fact. So the sine of x over x. Notice sine of x as x goes to 0 is 0. And as x goes to 0, x is 0. So you got 0 over 0. Downstream a little bit, there's a rule, like I've said before. If you've got 0 over 0 and you plug the functions in, that's going to be an opportunity to use what's called L'Hopital's rule. But we haven't dealt with that yet. So right now, we just got to deal with the circumstance here in some way. In the book, they use the squeeze theorem to make the proof. All I'm going to do right now is not use the squeeze theorem. I'll talk about that a little bit later. But right now, look what happens. The limit as x goes to 0. Notice I'm saying x now. I'm not saying theta. So I'm going to stay in terms of x. So as x goes to 0, this is what the function looks like. Tell you what, I'm going to go to my, let's go to Desmos real quick. Let's go to Desmos. And here's the graph of sine x over x, okay? That's what it looks like, okay? And notice at 0, it can't be because the 0 is denominator. So if you zoom in just a little bit, and if you notice that if you select and you travel in, are you guys able to see the graph, Desmos? Did you say yes, yeah, or a thumb up? Okay, great. Okay, so as you're getting closer and closer to 1, when you hit on the mark, it's undefined. There's a hole there because it is not defined at x equals 0. Can't happen. But as you come in from the right and as you come in from the left, that you're going to 1. So that's the definition. I'm going to go back to the iPad in a second and notice that at every multiple of pi, notice it's getting smaller. It's narrowing down how far away it gets from the x-axis, whatever the situation is there. But here at this point, right up here, it's undefined at that point. But so the definition of the the identity then is that the limit as x goes to 0 of sine of x over x, the limit as x goes to 0 of sine of x over x is equal to 1, okay? That's used in a lot of places. They use it in the text in a couple of proofs. And so it's going to be a value, but I'm going to ask you that there's several problems in sapling that you've got to use this technique, or this rule, okay? Well, here's the catch. This is something you can need a little practice with. And I've drawn the graph here just to remind you that if you come in from the left or you come in from the right, it's going to 1. So that is that. Now, look at this problem down at the bottom of the page. They do one in the book that's a little more complicated. We'll talk about it in a second. But if you take the limit as x goes to 0, look at this one now. The situation here is that the denominator and the value that you're taking the sine of, the angle you're taking the sine of, are exactly the same. They've got to be exactly the same. All right? Notice, in order to get to 1, notice in this problem, the value of the angle is 3x. The denominator is only x. So this is not equal to 1. So we need to manipulate the situation in some way to get, in order to use this identity, we've got to get the values in the angle and the denominator to be the same. But one thing I want to make a point of, and make sure you get this concept, okay? The angle, if I multiply the angle by 1/3, remember, this is a sine function. So if I'm changing the angle, that's not a linear change. If I multiply by 1/3, that doesn't make, it's not 1/3 of something. The angle is 1/3, but it's not, the distance and travel is not 1/3. The 3 in the denominator of this, you know, if I multiply the bottom by 3 and the top by 3, if I make that, you know, that to get the effect of 3x in the bottom, okay, so you'll see what I'm saying here. All right, watch this. So if I multiply the bottom by 3 to make it 3x along with the angle, I have to multiply the top by 3. So I do not multiply the angle. You don't change the angle to get the balance, you know, to get the same term, top and bottom. So notice what happens here now. So this is the limit as x goes to 0. We got to bring the 3 out front. And now I've got 3x in the bottom. And in the text, they have a tendency to replace that 3x with the t. Just so it's clear, the sine of t over t, that's equal to 1. If you got the limit as x goes to 0, the limit as x goes to 0 of sine of t over t, excuse me, limit of t goes to 0 of sine of t over t is 1. So as a result, remember this now, we can also use the fact that if you take the limit of a constant times a function, that is equal to the constant times the limit of the function. That's one of the rules we've got. And again, the book, they use t, and you don't have to do that if you don't want to. And once you got this down, it's a lot shorter process. This, if these two values are the same, this, the limit of this is equal to 1. As x goes to 0, the limit is equal to 1, okay? So what do we end up with? That means we've got a 3 out front. The limit as x goes to 0 is 1. The answer is 3, all right? So one thing I want to do is I'm going to go back to Desmos real quick, and you check it yourself, okay? But the idea is, notice what happens here if I say, what am I doing? Oh yeah, sine of 3x over 3x. Oh yeah. Notice what the problem we started with, sine of 3x over 3x is 1. The problem we started with didn't have a 3 in the denominator. Look at the answer is. The graph is approaching what? It's 3. And that's the answer we got here. So the limit as x goes to 0 of this function is 3. Verify it on your calculator, get that, you know, squared away. But that is something, the way to manipulate that is really important. You don't change the angle. You don't multiply by the angle. You multiply by the denominator and then out front of the function, okay? That's a big thing about, I wanted to get squared away on that. Okay, so what I want to do is go back here to see that. Any questions on that at all? Okay, tell you what, something I want to do, I want to go to Sapling, and I want to go through a slideshow that, a slide that's been put together, a slide arrangement. So I'm going to go to the new share and go to the desktop again. And let's go to Sapling. I think you're in a position now where you're seeing the screen and my screen, desktop, and I believe you're able to see the slideshow showing up. Anybody, yes?
Yeah, yeah, we see it.
Good. Okay. So take a look at this with me. Notice this, I'm going to kind of move through quickly. There's only just a few slides here. But section 1.4, dealing with the limits and continuity of trigonometric, exponential, and logarithmic functions. Objective. Use the squeeze theorem. The book used the squeeze theorem as the proof for the first limit that we were just talking about. And I didn't choose to do that. So I'll bring the squeeze theorem up later, but we're going to move on to the other stuff. Find limits involving trig functions, determine whether trig functions are continuous, and determine where exponential and logarithmic functions are continuous, okay? So look at the next shot here. So these were the main identities that I showed already. The limit is of the sine function itself as x goes to 0 is 0. Sine of 0 is 0. Cosine of 0 is 1. The limit as x goes to 0 of cos is 1. This is the one we just did, okay? This is an identity that's going to be a value. This one will come a little later. We're not worried about this right now. This one is being used in some proofs that we're going to talk about. So I wanted to make sure we got this and you got squared away with the situation, okay? So here's an example. This is similar to what we just did. They chose 2 theta. Notice what happened here. In order to get 2 theta on the bottom so that these are the same, they multiplied by 2 out here and 2 out front, all right? And here's what I said, they switch over to t to make it a little bit less cumbersome or whatever. But these two are the same. These two are the same. And as soon as you have that, this is equal to 1 if the limit is going to 0. Limit as t goes to 0 of this is 1. So this becomes the 2 out front, 2 times 1, which is 2 times 1, which is 2. Okay? Let me say this one kind of quickly. I think there's something similar that you're asked in Sapling. Check out what they do with this one. So in this one, you don't have a theta in the denominator. You got a sign on top and a sign on the bottom. So what they've done is they split this up to get the theta on the denominator up here and the theta in the denominator up here. So they multiply top and bottom by 1 over theta. They didn't change the angle, but they multiplied, that's like 3x, okay? And they multiplied by 1 over x and got this, all right? And so you can multiply the top and bottom by 1 over theta, that doesn't change anything mathematically. And now the goal is to get these to match. So if I multiply the bottom by 3, I got to multiply by 3 out front. If I got to get the bottom to be 4, then I multiply the bottom by 4, I got to multiply out front. And what we did before was we pulled the 3 out front on top, the 4 out front on the bottom. So that's really 3 over 4, 1 over 1. This is 3 times 1, 4 times 1. Notice they don't even do that right now. So you don't have to do every step once you get this down. But for right now, come to realize that this 3 out front is 3 times 1. This is 4 times 1, so that's 3 over 4. End result, okay? So when they present the problems, this is what they're referring to, okay? Any questions on that? Okay, 2 more quick slides. I think there's 2. All right, one other thing, it's talking about the continuity of the trig functions. Remember what we said, it goes forever to the right, sine function goes forever to the right, that wave, and the cosine goes forever to the right and to the left, both of them. So it's continuous for all real numbers, both of them. There's no value where there's a hole. When you just got sine on top and you got cosine on top, there's no problem. Every value can be plugged in from 0 to infinity, negative infinity to infinity. okay? And same with sine and cos. Tangent's a little different. Why? Because tangent is got a denominator. That means wherever cosine is 0, it's not defined. Tan is not defined. The tangent's not. So notice where that happens. Remember on our unit circle, when we were out at 1, 0, 1, 0, cosine was 1. We went up to the top of the unit circle at 90 degrees, or pi over 2, and the cosine, the x is 0. Or if you go down to 3 pi over 2, the x is 0. Therefore, cos is 0. So and 3 pi over 2 is the same thing. If you're going backwards on the unit circle, you're going to negative pi over 2. So at pi over 2 and at negative pi over 2, you've got vertical asymptotes. It can never touch that. It's not defined. The denominator is 0. And this is where that special curve for the tangent function gets repeated over and over and over again. And it's odd multiples. So it's pi over 2. The next one would be 3 pi over 2, 5 pi over 2, 7 pi over 2. And this graph is in between every stage of the way, okay? We're probably going to be working least with tangent. Sine and cosine are going to be used the most. But it's important you have the concept of where this is coming from, right? Okay, the last thing I want to mention is this. Exponential function, they're talking about e to the x, the function e to the x, all right? Remember, exponential function, yeah, that's e to the x. Remember also, 10 to the x is also an exponential function with a base of 10. But in this case, look at this, exponential function, it's continuous on its domain, which is all real numbers. Notice this, e to the x. E to the x is what you're looking at. Is there any value of x that causes the denominator to be 0 or illegal? No. So that means every value will work. And notice that at 0, e to the 0 is 1. E to the 1, remember, if you got e to the 1, if x equals 1, you're up here at e. And notice that's about 1, 2, where's 2? And here's 3, so 2.7, yada, yada. That's e. Remember, e is a number. It's a constant. It's just like pi, a similar thing like pi. So that's the arrangement there. But it's all real numbers. It's and the domain. When you get to log functions, log, log, which is base 10, or ln function, which is base e, remember, this is saying e to some power gives us this value of y. E to some power gives you this value of y. Well, notice this, that the answer, there is no exponent you can put on e to make it a negative, a negative answer. The situation is that the e to what power is, the x is what you're concerned about. Excuse me. So when you're talking about, let's go back to my iPad for a second, okay? The idea is, though, the answer can never come out negative. You take the log of something, let's go back to my iPad. Okay, so it's coming up momentarily. All right, so if you've got e to the x, remember, if you've got this situation, if you've got the ln of some value of the ln of x, the e is down here, and the circumstance is saying e to what power, this is this, equals x, okay? The power is here. Notice that this x, you're taking e to some power is x, that's what this equation is saying. There is no value you can put on this and make this number negative. E is positive. You put negative exponent, you put 0, you put positive exponents, x will never be negative. So that is the situation why, when you do the graph, x can never be negative, and therefore when you take the actual log, this value, x will never be negative. So it's always to the right. The domain has to be greater than 0 when you're talking ln, or if you're talking log, which is base 10. Right, so it's got some limitations to it. All right, and one last thing I want to mention is this. Let's go back. I want to show this about the slides. Oh no, that's it. That is the last. So we're moving into 1.5. That's going to be talking about tomorrow. So you guys make sure when you go to the problems that have to do with these, remember you need to get the denominator to match the value of the angle. And that's where you do the work. Show your work, come to class tomorrow, and everything will be cool. Any questions about this right now? If you've got questions, I'll address them tomorrow, okay? Any thoughts or questions at all? Okay, that's it for today. I wanted to go through that and make sure you look at the sapling 1.4 problems, dive into them, come in with questions, and we'll move on to 1.5. On Thursday, the plan of attack for the week now is class today presentation, this presentation. Tomorrow there'll be another presentation dealing with 1.5 and answering some things from 1.4. And then Wednesday again is going to be an office hour kind of opportunity. If you've got questions, come on. Go to office hours for your class. I'll have set up on Wednesday in week 2. And then Thursday, we're going to have a quiz. And it's going to be, it'll cover the 1.1 through 1.3 stuff from last week and a basic question from 1.4 and 1.5 from this week, all right? So if you've got anything specific that you want to clarify, feel free to stay after right now and talk with me. I'm going to log off and end the recording right now, all right? Any questions at all? Okay. Okay, so anybody have anything at all? Okay, I'm gonna go ahead and end the class then, all right?
Sounds good. Have a good one.
Be well.